In this video, we discuss refrigerators. A refrigerator is a device that takes heat from a cold place, usually the inside of the refrigerator, and releases heat to a warmer place, right? Usually the room. So this is a schematic of the refrigerator. It takes an amount of heat QC from the cold reservoir at a temperature T cold and releases some heat QH to the hot reservoir at the temperature T hot. And as you know, this does not happen by itself, and we need to power the refrigerator, and so it also takes some work to operate. And so as you remember, we have chosen the convention that W is the work done by the system. So here, the refrigerator does not do work on the surrounding like a heat engine, but instead it needs some work to transfer the heat. So W is negative in this case. We also use the convention that Q is the heat added to the system. So since QH is the heat rejected, then QH is negative, and QC is positive since this is heat that enters the system. So the net heat is QH plus QC, and since QH is negative, I can write that the net heat is minus absolute value of QH plus QC. Now, if we consider the state of the refrigerator, it operates in a cycle. So this means that after a full cycle, the refrigerator is in the same state as before the cycle. So the internal energy at the beginning of the cycle is the same as the internal energy at the end of the cycle. And so delta U is equal to 0. And we can write the first law of thermodynamics. Delta U is Q minus W. So since delta U is equal to 0, we have QH plus QC minus W is equal to 0. Or we can write this another way. We can write that the absolute value of W is equal to the absolute value of QH minus QC. Now, ideally, for the best refrigerator, you want that the work is the smallest, that is the smallest consumption of energy, and you want QC to be the largest, right? So the refrigerator takes the largest amount of heat from the cold place. So we define a coefficient of performance, K, as the ratio of QC over the absolute value of W, right? So the smallest work required will increase the coefficient of performance, and the largest heat removed from the cold place will also increase the coefficient of performance. And since absolute value of W is equal to absolute value of QH minus QC, then we can rewrite the coefficient of performance K as QC divided by absolute value of QH minus QC. Now, before we continue, you should note that this is not the same as the thermal efficiency for a heat engine, right? For the thermal efficiency, we have a maximum of 1, right? But here, the coefficient of performance can be larger than 1. So here is a schematic of the principle of a refrigerator. On the back, at the bottom, there is a compressor, and that will do an adiabatic compression. And so this is where your work is absorbed, right? To compress the gas, you need to do some work on the gas. As we have seen, during an adiabatic compression, then the temperature will increase. And this heat will be released in the room by the condenser. Then there is the expansion valve. This is where the gas will have an adiabatic expansion, and as we have seen, the temperature will decrease during an adiabatic expansion. And then the cold gas will absorb heat from the inside of the fridge, and this is done at the evaporator. And finally, this gas goes back to the compressor and runs in a cycle. And air conditioner works pretty much the same way, except that the entire room is the cold reservoir, and the heat is rejected outside of the room, usually outside of the house. For a heat pump, it also works in the same manner, except that in winter, it will take heat from the outside and reject heat in the inside. So the outside becomes the cold reservoir, and the inside becomes the hot reservoir. All of these are refrigerators in the sense that they move heat from cold to warm. In fact, sweating is also an example of a system that works as a refrigerator. We have already mentioned that the evaporation of sweat takes energy from your body, and so this is a way to cool down. But in this case, what is doing the work? What is doing the work in the process of sweating? It may seem like this process does not require any work, but when the sweat evaporates, then the air is saturated with water, so no more evaporation can happen. But because of wind, then the wind is moving the air, and it will make the humidity go away and replaced by some fresh air, and so that sweating can continue to happen. And so in this case, it is the wind that is in fact doing some kind of a work. Now finally, let me mention how our discussion on refrigerator will be related to the second law of thermodynamics. One of the versions of the second law of thermodynamics is that it is impossible for any process to have as its sole result the transfer of heat from a cooler to a hotter body. This is known as the refrigerator statement of the second law, or the Clausius statement of the second law. And so what this means is that you cannot transfer heat from cold to hot without requiring something else, right? As we have said, you need to do some work for this to happen. It's not going to happen by itself. So this statement is essentially saying that the work cannot be zero, right? A workless refrigerator is impossible.